voltage or signal amplitude versus time. But instead of a waveform display, ultrasonic instruments generally use pips to measure amplitude and time. Amplitude is indicated by the height of the pips. Time is the distance between pips. Other presentations frequently used include a plan view picture similar to that of an X-ray, direct reading meters, and digital counters, all of which are based on signal amplitude versus time relationships. By properly applying the system to a specimen and properly interpreting response indications, we can learn something about that specimen. You will learn just how this is done in the segments to follow. You'll find that ultrasonic testing has several desirable features. One being its high sensitivity or ability to detect small discontinuities. Its ability to penetrate thick materials. Its accuracy, for example, in measuring material thicknesses, locating discontinuities, determining their relative size. A fast response, permitting rapid and automated testing. It generally requires access to only one surface of a specimen. Materials that can be tested include metallic products such as aluminum or steel forgings, castings, pipe, non-metallic materials such as plastics and ceramics. Limitations? Yes. You'll find that excessively rough surfaces can limit ultrasonic testing. So can unfavorable geometry, such as complex shapes, contoured or angular surfaces, the size of a specimen, or an undesirable internal structure, such as coarse grain, porosity, high inclusion content. You'll learn the reasons why, as well as how to minimize their effects when possible. Briefly, ultrasonic testing involves these elements: test methods and tasks. Discontinuity detection, the determination of bond and thickness measurement. Also, specialized applications such as determining material structure, physical properties, hardness testing. For successful testing, personnel must have a knowledge of test capabilities and requirements, equipment selection and procedures depending on the selected test method, and the tasks to be performed. You'll find that all four tasks can be accomplished with pulse echo, where through transmission is more often associated with specialized applications, although it can be used to detect discontinuities. Part 1 of this training course introduces you to the fundamental properties of ultrasonic sound, what it is. Part 2 deals with how it is generated, and Part 3 covers the different modes of wave propagation, their characteristics. Part 4 introduces you to the basic methods and techniques used to couple ultrasonic sound to a specimen, and describes the advantages and disadvantages of each. Part 5 covers pulse echo and through transmission testing systems, instrument controls, accessories, and the various display presentations used. Part 6 continues with the use and application of calibration blocks and reference standards. It stresses the importance of calibrating and standardizing test instruments. And Part 7 describes various special applications of ultrasonic sound relative to non-destructive testing. It also covers the interpretation of test results and the differentiation between relevant and non-relevant indications. Our study of ultrasonic testing begins with basic concepts of sound. Of course, you know what sound is. It's something we hear, the sensation of hearing. The beat of a drum, the sound of a trumpet, clashing cymbals. All are examples of sound. Not only is sound heard, it can be felt, seen. Touch the cone of a radio speaker while it's operating. We feel the vibrations, see the cone move back and forth. Strike a tuning fork. Again, sound is vibrational energy, a back and forth motion, energy in motion. We know sound travels in air. We know sound can be reflected as echoes. We know water conducts sound, this being the basis for sonar, the detection of objects underwater. Sound also travels in solids. Shown here is a ball suspended from a string. Think of it as a pendulum. If we move the ball to the left, then release it, the ball will swing through an arc and back again through the same arc. We gave energy to the ball by raising it. The ball first moved in one direction, then in the opposite direction following the same path. The ball will continue to swing back and forth with diminishing amplitude, or until it's stopped. When the ball is moved from its rest position, we say the ball has been displaced. The maximum distance the ball moves from the rest position is called a displacement. The term also applies when the ball is released and swings to a new maximum position in the opposite direction. Similar displacements occur in all solid materials. Visualize hitting a solid rubber ball. First, the ball's surface was depressed inward. Then, it expanded outward, overshooting the original position. And though you can't see it, the surface continued to move back and forth for a short time. The distance the surface moved in from the rest position is a displacement. The distance the surface moved outward beyond the rest position is a displacement. The motion can be compared to that of a small mass attached to a spring. Let's call that small mass a particle. If we stretch the spring, then release it, the particle will be set into motion and vibrate back and forth, first in one direction, then in the opposite direction. Left to itself, the particle will continue to vibrate about its at-rest or equilibrium position, the driving force being the spring. We call this back and forth movement a cycle. To further illustrate the sequence, recall the ball suspended from the string. A pencil is shown attached to the bottom of the ball. We're going to tap the ball to one side and at the same time move the string horizontally in the direction of the arrow. See what happens. The pencil first drew a curved line away from the center line of string travel until a maximum displacement was reached. The line then swung in the opposite direction until a second maximum displacement was reached, at which time the line returned to the original direction of travel. Of course, the ball will keep swinging, and the cycle is repeated several times. Now that you have the concept of a cycle, let's consider the terms period and frequency, and their relationship to time. Period is the time required for something to move through one complete cycle, the unit of time normally being the second. Frequency is the number of cycles completed per second. Again, recall the swinging ball and pencil suspended from a string. If the swinging ball moves over the path A to B to C to D to E in 1 second, the period of the cycle is 1 second, the time required to complete one cycle. The frequency, then, is 1 cycle per second. Since Hertz is the internationally accepted term for cycles per second, we can say that the frequency is 1 Hertz. Here is another example of particle vibration in a medium. The distance A to B denotes the number of vibrations or cycles that take place in 1 second. 3 complete cycles are shown. The period of each cycle is 1/3 of a second. The frequency is 3 Hertz, the number of cycles completed in 1 second. Again, Hertz, abbreviated capital H, lowercase z, means the same thing as cycles per second. Here we have a thin plate positioned on supports. Now we see the plate vibrating after being struck by a mallet. Note that we have 2 things. 1, vibration, and 2, displacement. Consider the condition of a thicker material being struck by the mallet. Does vibration and displacement still occur? Yes. By feeling the material, we can sense the vibrations. And even though we may not be able to see the displacement, we know that both vibration and displacement have occurred. To visualize how these vibrations pass through a solid material, first imagine the material consists of a row of balls suspended as shown. Let's call the balls particles. If we displace the particle on the left to one side, then release it, the energy we give the first particle will be transmitted through the series of particles and finally affect the particle on the extreme right, like this. Note that we have had a succession of particle displacements, and energy has been transmitted through the row of particles. It is through this series of small material displacements that energy is transmitted through a solid material, or for that matter, any medium, be it gaseous, liquid, or solid. Sound can be generated in a number of ways. For example, if you strike a drum, its surface moves back and forth. If you hit a key on a piano, a string is set in motion. In both cases, you establish a vibration or cycle. And since the cycle is repeated, you get frequencies. The drum has a low frequency, approximately 50 Hertz. The top note on the piano has a higher frequency, 4,100 Hertz. Here's a man using a jackhammer. Lots of noise or sound is made, and you hear it. The up and down action has a definite frequency, and vibrations are transmitted into the material. This man is doing the same thing, only he's using something called a transducer. You can't hear the sound. Why not? Because human hearing extends only to about 20,000 Hertz, and the man with the transducer is using a much higher frequency, perhaps 5 million Hertz. This means sound extends beyond the range of human hearing. This sound we call ultrasonic sound, or ultrasound. Ultrasonic frequencies are normally expressed in kilohertz or megahertz. Kilo, added to hertz, means the figure preceding the term must be multiplied by 1,000. Mega, added to hertz, means to multiply by 1,000,000. For example, 27 kilohertz means 27,000 hertz. What do we mean when we say 5 megahertz? Since mega means 1,000,000, then 5 megahertz must equal 5 million hertz. Remember, 1 hertz is the same thing as 1 cycle per second. So far, you've learned sound is energy in motion, a vibration, not necessarily audible. The range of human hearing extending to about 20 kilohertz, the ultrasonic range being those frequencies above 20 kilohertz. We might add at this point that frequencies used in ultrasonic testing range from about 200 kilohertz to 25 megahertz and higher. That's 200,000 to 25 million cycles per second. And up to this point, we've talked of sound propagation as simply a succession of small material displacements, represented by a row of balls butted together. A more accurate description is shown in this illustration. Imagine that the medium consists of many individual particles kept in position by springs. elastic forces. We apply a vibrating force to the left side. The particles in the first plane begin to vibrate back and forth. The springs, or elastic forces, transmit the oscillations to the particles in the second plane. When these have started oscillating, the vibratory movement is transmitted to the third plane, the fourth plane, and so on. This creates zones where the particles approach each other very closely, and other zones where the particles move away from each other. It is via this wave, advancing through the medium, that energy is carried. The particles themselves do not move through the medium. Visualize that the balls shown here represent the internal structure of air, water, and steel. More balls are shown in the water than in the air, and more in the steel than in either the air or water. If we displace the ball on the left and release it, we start a sequence which ends with an effect on the extreme right-hand ball. Notice that it will take time to swing through the distances between the balls, the distances being greatest in the air. The closer together the balls, the faster the energy travels. It is a similar variation in particle density, plus the elastic properties of a medium, that determine the velocity of sound. Because of differences in elasticity and particle density, the movement of sound isn't the same for all mediums. For example, the velocity in steel is about 4 times the velocity in water, 19 times the velocity in air. Here is a transducer positioned in water. Visualize, it acts like a piston moving back and forth at a specific frequency. As the transducer vibrates, sound energy is transmitted into the water. This energy moves through the water at a specific velocity, the velocity being constant. Now, let's place a steel specimen in the water and see what happens. The sound energy traveling through the water strikes the steel. Some of the energy enters the steel. Within the steel specimen, the velocity is also constant, but it isn't the same as the velocity in water. Why? Because the steel's particle density and elastic properties are not the same as that of water. Velocity is constant for a given medium, but different in different mediums. When something is dropped on a water surface, a series of waves form. The distance between the peak of the first wave and the peak of the second wave is a wavelength. It is also the distance between the 2 adjacent valleys, 2 adjacent points in the same state of motion. You'll recall that waves traveling through a medium create zones where particles approach each other very closely, and others where the particles move away from each other. Here, wavelength is the distance between 2 adjacent planes in the same state of vibration. The distance a wave advances while a particle completes one cycle. Again, visualize that a transducer acts like a small piston near the surface of the test specimen. As this piston moves back and forth at a fixed frequency, striking the specimen, small areas within the specimen are periodically displaced. The vertical line 1 denotes such an area of maximum displacement moving through the specimen. Here we have a distribution of maximum displacements caused by the piston or transducer. Note that the first maximum displacement has moved forward and is followed by additional maximum displacements of equal wavelength. The symbol for wavelength is the Greek letter lambda. It is important you know wavelength, lambda, is equal to the ratio of velocity to frequency. That lambda equals v divided by f, where lambda is the wavelength, v the velocity, and f the frequency. Velocity being constant, wavelength is shortened by increasing the frequency, lengthened by decreasing the frequency. For the moment, let's ignore the actual units for velocity, frequency, and wavelength, but see what happens with simple numbers. If the velocity and frequency are both equal to, let's say, 10, Then the wavelength, which is the ratio of velocity and frequency, would be equal to 10 divided by 10, or 1. But if the frequency is reduced or lowered, for example, to 5, the wavelength will be increased or lengthened. Reducing the frequency by 1/2 increases the wavelength by 2. Further reduction in frequency to 1/10 its original value causes the wavelength to increase by a factor of 10. Again, wavelength, lambda, is a ratio. The top number of the ratio is a fixed value, this being the velocity, v. The bottom part of the ratio is a variable, this being the frequency, f. For a given ultrasonic test, different test frequencies may be used. And as the test frequency is changed, so is the wavelength. These relationships will be explored more fully in the discussions to follow in Part 2 of this training series. Before we continue with transducers and the generation of ultrasonic sound, let's briefly review some of the major points covered in Part 1. First of all, sound is vibrational energy, a back and forth movement, energy in motion. Sound energy travels through a medium as a series of small material displacements.
See how non-routine maintenance is handled, let's follow a typical United flight as it passes through both maintenance and non-maintenance stations.